My name is Jose Villazon, and this is my Physics 1 Lab 4. For the introduction, our purpose in this lab is to explore the oscillating motion of a spring and mass system in 2 dimensions, and some models and fundamental principles we'll be using. As the last couple of labs, we'll be using the position update formula and the velocity update formula, which have the pictures there. And then, for this lab, we'll be using the kinetic energy formula, which is 1/2 m times Vf squared minus Vi squared, and then the potential energy formula is also new for this lab, which is mg times delta y, and then we're also going to be using the spring potential energy formula, which can be calculated by doing 1/2 k sf squared minus si squared, and then the force of gravity, as we've used in the past, is Fg equals minus mg. And then the spring force is minus k magnitude of L minus L naught times L hat, and then Newton's second law, which we've used for every single lab, F net equals dp dt. And a little preview of our results, that our model will closely predict our experimental data. So for the experiment, we define that the system is the mass in the spring and the surroundings were just the air. And then from the tracker data, we got that the ball's mass was 0.402 kilograms and the velocity started at 0, and its initial position was at negative 0.108 and negative 0.634. And then we also, the time started at 0.475, and then we have a delta t of 1 divided by 210. Okay, so now for the code. Starting over here, we have the gravitational constant 9.8, and then we calculated the spring constant to be 6.83 Newton meters, and we calculated that the relaxed length of the spring was 0.123, and then here we calculate that L is the position of the ball minus the position of the spring, and L hat is L divided by the magnitude of L, and then S is the magnitude of L minus L naught. And then, as we saw in the introduction with the different energy equations, we just plug in the relevant values into those equations here, and then we add them all up using the energy principle. So now going into the calculation loop, we set these things over here to the initial energies, and then we calculate the force of gravity and the force of the spring, which we also saw on the introduction slide, and then we add them using Newton's second law right here. And then we have the velocity update formula, and then the position update formula for the ball, and then again we recalculate the L hat, and S, and then after doing that we calculate the energies again and then find the change in energy. So the change in kinetic energy, the change in potential energy, the change in spring energy, and the change in total energy. So for our model versus experiment, we can see that the model predicts the X position pretty well. You can see in the video that's the output we had. And for the Y, you can see it's a bit off. I'll go into this in the possible errors, but I think my tracker data was slightly off, so that's why the model is like slightly above where the experimental data was. Possible source of error. One obvious source of error I had was my tracker data for the Y position was off by a little, so that was why the comparison graph was slightly offset. This main question, it asks for your model, is the energy principle satisfied? And yes, because it is, because the energy principle is satisfied since there's no outside forces acting on the system, so therefore the change in energy will be 0. We can see that there are many types of energy in the system, but the graph clearly shows that the change in energy is always 0, as you can see there. Part of the what does this mean question, we're comparing the oscillation periods of the X and the Y. So from the data, the oscillation period for X was 1.614 seconds, and for T it was and for Y it was 1.52 seconds. Since these values slightly differ, it would affect our calculations for things like the spring constant, which would be off by a noticeable margin.